Let's start with a simple illustration of a combat game tutorial segment, where players battle waves of minions, earn experience points, and level up after fulfilling certain requirements. We will begin by taking a look at how the game design document is constructed for this game. The first column of the GDED represents the current wave of enemies. The yellow columns display the minions' stats on each wave, the number of minions, the likelihood that a player will kill a minion, and the average number of minions slain every wave. Since the first 30 waves of enemies represent the game's tutorial, the number of minions per wave and the chance of killing a minion remains constant. The green section models the experience gain flow of the game. For each minion slayed, players are awarded 30 experience points. The estimated total XP gained at the end of each wave is tracked in the cumulative XP column, which adds the current wave's XP to the previous points. The next column, in red, displays the estimated level reached by the player at the end of each wave. As a result, we can observe that it has been estimated that players reach level 2 at the end of wave 2. Furthermore, once the last tutorial wave is completed, players are expected to reach level 18. Lastly, the experience point thresholds required for a level up are kept in the purple column. Level 2 requires 100 XP, Level 3 requires 120 XP, Level 4 requires 144 XP, and so on in an exponential progression that ends at level 30. To represent the spreadsheet's data, we will leverage the power of Machinations' intuitive nodes and connections. Moreover, we will use the resource tokens of our diagram to represent the number of minions, as well as gained experience points. The first step of constructing a diagram is to clearly define the system's inputs, outputs, and functional parameters, such as simulation step representation. To model our game, we will use the GDD data and define one simulation step as one wave. As such, for each simulation step, the diagram will refer to each row of the document and use the relevant number of minions, kill chance, XP gain, and estimated XP. We will start with the yellow section, minions spawning. The first column, minions per wave, will be modeled using an automated source node and an output resource connection with its formula set to 5, representing the number of minions that need to be spawned. The 60% chance for players to defeat each minion is translated to a random gate node and its corresponding connection that sets the kill chance for each token passing through the gate. The next column, minions killed on average, is represented by the storing pool, minions killed. The key difference between the two is that the Machinations pool uses an actual percentage for the number of slayed minions instead of an approximative formula. Once we modeled the number of minions killed during waves, we can start computing the accumulation of experience points achieved by players. Since each minion slayed awards 30 experience points, we can use a state connection that stores the number of defeated enemies and multiplying it by 30 using a register node. Since XP gain in each wave is now stored in the register, we can create an output state connection that transfers this value to a cumulative XP pool, which has the same scope as the green GDD column. Finally, the next system we need to tackle is leveling up based on the required experience points. To check if the player accumulated sufficient XP to reach a new level, we will construct the level up check register that compares the actual XP with the level up requirement. When enough experience points are stored in the cumulative XP pool, a conditional state connection will enable the level up source that generates a level token representing the current level stored in the red pool. The last step of the diagram is to compute the level up requirements saved in the purple column of the GDED. To achieve this, we will use a state connection that sends the current level to the computational register. The register utilizes the same exponential formula as the purple column of the GDD, using the current level to set increasingly difficult requirements. Once the level up XP requirements column has been modeled, we can use its results to send the thresholds for the level up check register. Now the diagram is completed. All the GDD columns are now associated with a Machinations node and their subsequent connections. The main takeaway from a mental model migration between GDD and Machinations is the following. Sources generate resources, pools store them, gates control chance-based events, registers transfer spreadsheet formulas into the diagram, and each simulation step can model each row of the GDD. Once our progression system has been modeled, we can view our GDD come to life by simulating the diagram. Press Predict and Machinations will simulate multiple playthroughs, recording all the relevant parameters for each player. All the simulated data is available in the Machinations chart, where you can use statistical indicators to gain data-driven insights on the player's progression. Upon investigating the chart, we can observe the following surprising result. Of 100 simulated players, at the end of the game's tutorial, only 5% of them reached level 18, as predicted in the estimated level column of the GDD. The rest of the 95% of the players performed better than estimated by defeating more minions than the proposed average, and managed to reach level 19 and even level 20. Unforeseen scenarios in the GDE. Additionally, by following the progression of the players' levels in the chart, we can gain insight into the exact wave in which players reached a new level, highlighting both experienced players and more casual ones. To find out more about how Machinations can enhance your experience with game design documents, visit machinations.io and start your journey.